la présentation suivante, histoire de tenir le planning de la matinée. C'est les équipes du bureau Veritas qui vont vous présenter Hydrostar. Hein, donc, on parlait du temps de calcul pour la conception, enfin, quand ça prend une semaine. Enfin, l'ingénieur, il a besoin aussi d'un outil qui marche très rapidement pour les calculs de tous les jours. Et c'est le cas d'Hydrostar qui est très utilisé en tenue à la mer, hein, développé par le bureau Veritas et utilisé à la technique hydrodynamique aussi de façon très régulière.
Oui, merci, Chairman. Je m'appelle Chen Xiaobo. J'avais fait une thèse à Centre-Nantes il y a longtemps. Ensuite, à IFP, 2 ans, avant d'entrer à Bureau Veritas en 91. Je travaillais toujours en tant que chercheur, développeur pour locaux d'Hydrostar. C'est la première fois que je suis présent au ATMA. J'ai le plaisir de vous présenter les résultats récents que nous avons pu obtenir pour la tenue à la mer, comme Chairman vous a présenté. C'est un problème très complexe que je vais vous montrer en introduction. Et aussi, je me permets de vous présenter sur des pages en anglais, puisqu'on m'avait dit, pour traiter un problème compliqué, il faut utiliser un langage plus simple. J'aime la langue française, elle est très belle, elle est sophistiquée, mais j'aurais préféré un langage plus simple, si vous me tolérez. So, oui. Ah oui, c'est là, pardon. Donc, il y a un plan de présentation, je vais passer vite l'introduction sur le besoin et les méthodes existantes. Et ensuite, on n'est pas content des méthodes existantes et nous avons développé une nouvelle approche et quelques résultats et les perspectives de notre travail. Sorry, I switch on English. So, for the seakeeping problem, for Bureau Veritas is critically important because we have objective to make shipping safe. For that, we usually apply just rules. And now, more and more today, besides the rule application, we use what we call the direct computation as well to certify, to approve some concept, some designs. So, seakeeping is one of critical methods we need to compute, of course, the ship behavior at the sea and also the wave loads on the structure, and also now more and more requirement on the resistance as well. One of typical issue is we have the trouble is to estimate the fatigue damage in a reliable, accurate way. We know the wave load increases with speed, and also speed will increase the encounter frequency if at sea. And the fatigue damage is proportional to the loads power 3 and 5. That means if we increase 30% of fatigue loads, our fatigue damage will be doubled or even more. In other words, if our tools have the error around 30%, our maybe final result estimation of fatigue damage will be totally wrong. So for seakeeping, of course, as previous presentation, a lot of progress have been made by using safety. Safety is wonderful, can give us many physical insight to that. However, here we like to stress on our routine application. We prefer some practical tool with error, controlling the error. So we are more, besides, also in BV we have safety tools as well. And besides safety, we like to make advance on the potential theory, which is classical and showing that is importance. So for the CKPin concern, we have very traditional strip theory, which is developed under the slender body assumption, and also the forward speed is taken into account by considering just encounter frequency. We call that is often encounter frequency approximations. And also, we have used the 3D hydrostar zero speed option to implement the similar theory like strip theory. So that is one thing that is still useful for today. Besides that, we have a green function method. We call that Neumann-Kelvin type. This many progress on that. However, we are more and more consider this method cannot give us the convergent results. So that's why we have more and more people developing on the ranking panel method. In this method, we don't use very complex green function, but use just ranking system. So in this method, however, we have to make the mesh on the free surface until 10 times, even 15 times of the ship length. So that's quite time consuming and other difficulties. However, this method is more give quite good results. And in our French community, many work have been done in this approach, but until today is always based on the Neumann-Kelvin type of green function method. In this method, one of critical, I think, if that is not the most critical issue, is we have a fundamental solution which is singular and highly oscillatory. This is not the case for the zero speed. When we have a speed, even as small as that is, we have this behavior. So here is an example what we have worked. Yan should be remember. We have worked together at the time in 2001. We have used the Neumann-Kelvin green function method for the slender body like Wiggly number 3. We have very good results. However, when the ship is a little bit fat, so we have this type of behavior. So numerical result is not convergent compared to the model test. So we have worked also on the other side, as I mentioned, the ranking panel method is give quite relatively good results. However, the waves is not very well represented, but that doesn't matter. But I can give fairly good results on that. The only problem of this ranking source method, if they solve the challenge, so still we need, it's not practical if we need 18 or 14, 40 panels on the free surface. It takes time to compute that. So that's why we stick on the green function method, and we have worked a lot on the reason why the previous green function method cannot work, and now we have made many renovations in this method. I summarize, there is 7 points of that. Among them, some are just technique. We can use them for other applications. That's direct and spirit from the other method. And some are really inept. I will explain to you. So for this problem, we have very basic equation is Laplacian. So our flow, which is assumed is rotational, and so exists the potential. The total potential should be satisfied Laplace equation. What's complex in our business is the boundary condition, in particular boundary condition on the free surface, which is nonlinear and very complex. So traditionally, we have to linearize this boundary condition on that. So the problem of linearization, there is some variation of that. So we decompose the total flow by a base flow and very steady. Base flow is steady. So the first two terms are steady part of the flow. And what we are interested in is the unsteady. Unsteady, that means is time harmonic flow. So this flow is on top of the steady flow. In the past, what we have done is we choose the base flow is uniform stream. With this assumption, the boundary condition looks simple, but however, that solution is not convergent. So more and more people use to choose a more physical acceptable base flow. For example, the simplest is double body flow. We call a ship-shaped stream, that is a current, however, avoid the ship. So the boundary condition on the ship for the steady flow is satisfied in this base flow. This linearization have never done before in our green function method. So we do that. So the boundary condition with this ship-shaped stream become like that. It looks very complex. You have unsteady potential, vertical derivatives, and horizontal derivatives always linked with base flow, with steady flow. So W linearly and also quadratically. Of course, this W is base flow, we compute that once. However, this boundary condition is quite complex. Complex in one sense, however, there is one feature is this W is quite local. We have tested the volume of W and its derivatives is very, very local. So we need this complex condition applied only in the vicinity of the ship. That is the one good feature. There is another good feature is this complex boundary condition on the free surface give us a boundary integral equation simpler. I will show you why. So of course, this is just test about this base flow, which is really local. We don't need to go very far. Another ingredient, very important, is the green function itself. So the green function with forward speed is very classical. Many people have done that. So this green function, in fact, is the potential flow generated by a source point. So source point, for example, in the origin of the ship, here is, you cannot see very much. Here is constant phase. So you have very complex wave system. So this complex system is represented analytically by the green function. If we use ranking source pattern method, this waves is very, very difficult to be represented, if not impossible. In other words, you need to mesh very, very fine ranking source on the free surface to represent the wave system. I can show you the animation or not. Just click on there. So this and click on there. This is some representation of the wave system represented by green function. So that's the very advantages of the green function can represent very well the physics. On the other side of the coin is this classical green function is singular and highly oscillatory. So if we use this green function on the free surface, we have trouble. That's why we have changed this green function Oh, there is a page. Okay. Anyway, we have modified the screen function by introduction of the viscous effect, which is based on the analysis of the Navier-Stokes equation and the linearized the condition on the free surface. We find we have additional term representing the viscous effect. So our classical green function is like that. And now with new green function, the Heine oscillator is heavily damped and the singularity is just removed. Here is a pattern of the green function for a source point on the free surface. So we can use this green function for our problem. So with the boundary condition on the free surface very complex, and we have a new green function, we just apply the classical green theorem. For that, we can establish the boundary integral equation. What's interesting is this boundary integral equation, we have not waterline integral anymore, which is troublesome, our nightmare in the classical nomenclature method, and we have not. So that's the benefit of complex boundary condition on the free surface. Another feature is we need the integral on the free surface. And on this free surface, we just locally, close to the ship, we need to do that. So we have a boundary integral equation on the ship hull on the free surface. Normally, that is okay. However, we find our boundary integral equation is not well conditioned. So in addition, we apply this boundary integration for the field point inside of the ship, in particular on the water plane. In such a way, all irregular effects are removed. Here is another technique about integration, because integral equation is constructed by the influence coefficient. This influence coefficient is the integration of the green function on the panel. So we do that analytically on the panel and on the double panel as well. So we have a very well accurate algorithm to compute green function itself and that's the integration on the panels. Here is some validation with previous work by students in Nantes. And also we have checked our viscous green function and that's the integration on the panels. What's the sensitivity of viscosity coefficient on that? We have checked if the coefficient of viscosity is changed, the integrand of our business is modified. Oscillation amplitude is larger when the coefficient is smaller. Smaller amplitude becomes smaller when the coefficient is larger. That's physical. However, the integration of that doesn't change. That's a good. So that means viscosity, in fact, is not important for global behavior of the ship. That is important in our intermediate computations. Also, we have used the technique to regroup the flat panel into a curved patch to be able to evaluate the tangent derivatives of the unknown. And as I mentioned, we have applied additional condition, our equation, inside the ship to ensure our green theory is satisfied fully. So in such a way, we remove the irregularity of the problem. So that's what, the last but not least, we find in the classical formulations, we have forgotten very important quantity. We call that is speed effect restoring force, which is created by steady flow. When ship in motion in the steady flow, there is a stiffness or restoring force against your motion. This stiffness in the vertical side is dominated by hydrostatic. This speed effect restoring force is represent or between 4 and 8%. That seems very small. However, with this small correction, which should be taken into account, we have much better comparison with motor test. If without, I should be less agreement. So I have to go to on the numerical results. Firstly, we have done many validation with submerged sphere, for which we have semi-analytic solution. Excellent agreement. We have also for the slender ship, like Wiggly 3, perfect agreement. What's the important is Wiggly number 4. We have breadth over length is 1/5. What's quite fat. That is, in this case, the classical nomenclature method fails. So for that, we have done convergence test and evaluate radiation coefficient, excitation node, and the motion RAO. Here is the Wiggly 4 with the mesh on the hull and water plane and on the free surface. So this is the Reeve added mass, Reeve, damping, pitch, added mass, and damping. So you have samples, square and triangle, represented by the model test. And you have 3 curves. I call that is hydrostar origin. Hydrostar origin, that means is the encounter frequency method, which is similar to the strip theory, but extended to the 3D. And you have blue line representing the classical nomenclature method. And finally, the red line represents our new method. So in particular for the added mass in Reeve and the pitch, the agreement of new method is perfect. For the damping, the very good agreement obtained, less perfect, but compared to 2 other methods, that's nothing comparable. And also for the coupling Reeve and pitch and Reeve coefficient is like that. And also for the diffraction nodes, 3 methods and benchmark result, and the motion RAO in Reeve and in pitch. So we can see our really new method in excellent agreement with benchmark. And in counterfocus approximation, our classical nomenclature method, they have a big discrepancy on that. So in conclusion, we have really, how to say, in some sense, revisited the problem and try to stick on the green function method. This method have 2 major advantages. One is the shift wave, the free surface effect is represented by Fourier representation exactly. The second, this method uses less partners, so that is efficient. So in this new development, we have summarized some particularity. One is, of course, we have chosen ship-shaped stream as base flow. We have developed a boundary integration free of waterline integral, and we have applied inside the ship as additional equation to remove irregular effect. On the other side, we have developed the green function with viscosity and analytical integration on that. And the last, we have reformulated the pressure and the loads by pick what we have forgotten and improve our comparison. And here is some near future items. We are working on the shear force bending moment along the ship. And also we like to have the ship wave patterns around the ship, which is useful. And of course, added resistance in waves. And in the future, maybe middle future, we like to combination of the other method with this green function method. If we master well this green function, which is valuable, more physically valuable at some distance from the ship. Because near the ship, you have many filament, nonlinearity, and large motions, which is better to use other methods to do that. So that is our planning for our work. Thank you for your attention and your comments and questions. Merci beaucoup.
Est-ce qu'il y a une question?
Oui, Yann.
Yeah.
Non, ici, je vais utiliser la méthode de la fonction green. Si, au contraire, parce que nous linéarisons la condition aux limites à la surface libre basée sur double modèle au lieu de uniform flow. Si c'est uniform flow, on n'a pas besoin de facettes sur la surface libre. Or, on a une intégrale de ligne. C'est ce que nous avons fait il y a 20 ans. Et là, on n'a pas l'intégrale de ligne, mais on a besoin de l'intégrale sur la surface libre près du corps. C'est un maillage sur la surface libre. Ouais. Mais tout est linéaire. Le potentiel aussi, c'est linéaire. Bon, bien sûr, la fonction satisfait une condition limite linéaire sur la surface libre. Elle satisfait la condition indépendante du double modèle. Il satisfait la condition, c'est une source. C'est une source. Il satisfait la même condition que Neumann Kelvin. Ça, c'est la condition satisfait par potentiel, mais j'ai omis la condition sur de la fonction green. Il y a ce thème-là, et aussi ce thème de suivant x et ce thème suivant x. Stop there. So la fonction green satisfait en effet la même condition qu'avant, comme Neumann Kelvin.
Il y a bien des conditions d'influence aussi sur des mailles de surface libre.
Oui.
Le fait que la fonction green satisfasse qu'une partie simplement de la condition de surface libre permet, une fois qu'on la réinjecte dans la condition, il reste des choses sur la surface libre, mais qui sont très localisées tout près du corps. Alors que la partie loin du corps, en fait, elle est satisfaite par la fonction green, qui satisfait ce qu'on pourrait appeler un champ lointain, et le champ proche, lui, n'est pas satisfait. Donc on reste avec un maillage de surface libre, avec des inconnus sur la surface libre, mais qui restreint très près du corps, et donc ça fait un... Dans les essais que tu as fait, il y avait à peu près le même nombre de mailles sur la surface libre et sur la carène. Alors que c'est un ratio 10 dans les méthodes Rankine. Oui. Oui.
Exact. Ah oui, l'introduction.
Mais c'est pas une viscosité normale, c'est une...
À l'origine, oui. À l'origine, on est basé sur Navier-Stokes equation. Ensuite, on fait des transforms Fourier, Laplace, pour arriver à identifier. Ah oui, d'abord, avant transformation de l'intégrale, on a décomposé l'écoulement total en une partie potentielle, irrotationnelle, et une partie rotationnelle. On voit bien que la viscosité est liée à la partie rotationnelle, mais on pourrait trouver ces effets-là dans la partie potentielle aussi. Donc, il y a un thème, théoriquement, c'est physique, qui influence la partie rotationnelle par la viscosité. C'est un travail avec Diaz que nous avons fait il y a 10 ans déjà. On a une condition sur la surface libre pour l'écoulement potentiel avec la vraie viscosité. Par contre, dans cette affaire-là, nous avons oublié la partie rotationnelle. il peut être important dans la physique. Mais nous, on limite seulement sur la partie irrotationnelle, avec la vraie viscosité.
Juste peut-être pour conclure, là vous avez eu en 20 minutes un résumé de 20 ans de travaux. Hein. Donc c'est pour ça que ça allait très très vite, que c'est hyper dense, et que si la plupart d'entre vous n'ont rien compris, c'est juste complètement normal. Pour ceux que ça pourrait intéresser, je vous encourage quand même à aller lire le mémoire qui fait une vingtaine de pages et qui est très synthétique, mais dans lequel il y a déjà plus de détails. Et puis ensuite, faut renvoyer sur l'ensemble de l'œuvre de Chiabo. Effectivement, les papiers qu'il a publiés avec Dias sur la fonction de Green et les visqueuses, il y en a eu des dizaines. Les papiers sur l'introduction de la vitesse d'avance, etc., il y en a eu plusieurs aussi. Donc là, on a condensé, très 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 condensé. Donc voilà, c'était juste du teasing pour aller vous faire lire autre chose.
Oui, il y a un certain nombre d'années avaient été développées des méthodes de couplage, éléments finis, représentation intégrale. Vous n'avez pas cité ces méthodes. Quel est l'avantage de votre approche par rapport à ça?
Cette approche-là est limitée à la fonction Green, qui fait partie des méthodes de frontières, des méthodes de singularité. Et effectivement, par ici, sous l'Insta, à l'époque, il y a Jamy et Ofra qui ont travaillé sur les éléments finis localisés. Et ensuite, il y a un autre courant qui dit que ce serait bien de les coupler les deux. Je crois l'avantage d'avoir éléments finis localisés, c'est prendre en compte les non-linéarités près du corps. Ça, par la fonction Green, on ne peut pas. La fonction Green, seulement traiter le problème linéaire. Le couplage avec les deux, c'est ce que je souhaite de le faire dans le futur, comme j'ai dans la perspective. Ici, on ne voit pas très, très clair. On voit bien, oui, ici, c'est un CFT, hein, en l'occurrence, de éléments finis localisés. On voit bien, ah oui, on voit de l'autre côté, on voit mieux. Si on utilisait le CFT localisé, ou élément fini localisé, les champs de vagues, ils perdent sa trace à une distance relativement courte. Donc le mieux, c'est de coupler avec les méthodes éléments finis ou d'autres différences finies, souvent le CFT, localisées avec la méthode potentielle qui décrit les vagues exactement. C'est pour ça qu'on aura une méthode beaucoup plus fidèle à la physique. C'est ce que je voulais dire. Mais aujourd'hui, on n'est pas là. Aujourd'hui, c'est seulement la fonction Green. On a besoin d'un PV, un outil rapide et fiable pour les utilisations quotidiennes.
Une dernière question? Non?
Ça prend beaucoup plus de temps numériquement avec de préparer le calcul avec cette fonction Green ou avec cette méthode
par rapport à la ranking, ça c'est sûrement supérieur. Il suffit de voir à zéro vitesse d'avance. On utilise la méthode fonction Green. On n'utilisait pas la ranking. Mais pour nous, vitesse 0 avec vitesse, ça doit être plus compliqué que zéro vitesse. Si zéro vitesse, c'est pas comparable, oui, l'autre, c'est facile à 10 ou 20 fois plus long, la méthode ranking. Ici, c'est bon, actuellement, pour les calculs, je peux vous dire, c'est une demi-heure par fréquence. On peut le réduire en 10 minutes, a priori, mais ce n'est pas encore jusqu'à là. Mais une méthode ranking, le minimum, ça doit être compté en plusieurs heures pour le même calcul. Mais c'est encore maniable par rapport à CFT. CFT, chez nous, c'est compté en semaines. Donc c'est encore mieux parce que c'est basé sur la théorie potentielle qui est moins fidèle à la physique, mais on prend le principal. Effectivement, c'est un compromis. Bon.
Voilà. Encore merci beaucoup.
Merci.
qu'on va clore cette séance sur l'hydrodynamique.